Web services are an essential part of the modern Internet. They enable web applications to interact with each other, regardless of what platforms or programming languages they are written in. This makes web services a valuable tool for developers who want to create flexible and scalable web applications. Web services are used in a wide range of applications, including e-commerce systems, banks, mobile operators, and web stores. For example, e-commerce systems often use web services to process payments, deliver goods, and provide customer support. Banks use web services to provide financial services such as banking, loans, and deposits. Mobile operators use web services to manage their networks and provide services to their customers, and web stores use web services to catalog products, process orders, and deliver goods. The significance of web services is growing every year, so it is becoming crucial to ensure the scalability of web services, that is, the ability of the system to increase the processing amount with the increase in the number of users. The application of artificial intelligence to automate the scaling of web services is an active area of research. Scientists and engineers are developing new AI methods and algorithms that can help improve the efficiency and accuracy of automated scaling in microservices architecture. MSA offers numerous advantages in terms of flexibility, scalability, and service independence, but it also introduces complexities associated with managing these distributed systems. Utilizing design patterns in MSA becomes exceedingly important as they offer ready-made and proven solutions to such challenges. Patterns help find optimal ways to manage data consistency, implement service-to-service relationships, monitoring, and scaling. They contribute to the creation of stable, efficient microservices applications, allowing developers to focus on application functionality rather than solving complex technical tasks. In microservices architecture, some design patterns have become extremely popular and widely adopted. SAGA, Segregated Access of Global Atomicity, CQRS, Command Query Responsibility Segregation, API Gateway, and Circuit Breaker. In MSA, where system components are divided into separate services, situations may arise where one service successfully makes changes to the database while another service, depending on these changes, has not yet updated its data. This can lead to inconsistent data state in the system. Additionally, problems may arise during the execution of distributed transactions. To address issues with distributed transactions, the SAGA design pattern is used. This pattern is based on the idea of breaking down a large transaction into smaller subtransactions, which are executed separately in each microservice. If one of the subtransactions fails, a compensating transaction is applied to undo or adjust the changes made by the preceding transactions. Complex queries contain a large number of table connections and can block tables, preventing any write or update operations until the query is complete and the database unblocks the tables. Database read operations are usually performed several times more frequently than write operations, and in systems with intensive transaction execution, this problem can be exacerbated. The CQRS, Command Query Responsibility Segregation, pattern divides one object into two objects. So, instead of executing both commands and queries for one object, we split this object into two objects, one for the command and one for the query. A command is an operation that changes the state of an object, and a query does not change the state of the system, it just returns the result. For example, the database can be divided into two logical representations, one for commands and the other for queries. When using two physical databases in CQRS, a replica is created from the primary database. Microservices can communicate directly with each other without the need for a centralized manager. However, as the MSA system evolves and becomes more mature, and the number of microservices gradually increases, direct communication between microservices can lead to significant overheads, especially for calls that require multiple round trips between the API consumer and the API provider. A more efficient approach to addressing these issues is to use the API gateway pattern. Here, all microservices communicate with each other, receive API calls from consumers, and then transform the received data into a data structure and protocol that API providers can understand and process. Using the API gateway significantly reduces direct one-to-one communication between services. Additionally, microservices are relieved from the code required to perform tasks such as API contract mapping, service discovery, and tasks related to controlling and providing access to system resources, authentication, authorization, accounting. The circuit breaker pattern is a design pattern used in microservices architecture to prevent a system from making calls to a service that is likely to fail. It acts like an electrical circuit breaker, automatically detecting failures and preventing the application from attempting operations that are likely to fail. This pattern helps to maintain system stability and resilience by preventing cascading failures in distributed systems. The SAGA, CQRS, API gateway, and circuit breaker patterns help address typical challenges in developing and managing microservices applications, ensuring improved performance, reliability, and ease of maintenance. MSA microservices architecture. Systems are inherently complex due to numerous dependencies and interrelations in their operation. Therefore, models of artificial intelligence, AI, machine learning, ML, and deep learning, DL, can detect these dependencies and make predictions. Popular models of AI artificial intelligence include neural networks, convolutional neural networks, CNNs, regression models. Linear regression, polynomial regression, logistic regression, multi-class classification models, K-nearest neighbor algorithm, KNN, support vector, machines algorithm, SVM, naive Bayes classifier algorithm, decision tree. Recurrent neural networks, RNNs, nonlinear non-parametric autoregressive model with exogenous inputs, NNARX, long short-term memory, LSTM, gated recurrent unit, GRU. Having analyzed the core concepts and approaches used in MSA and ML, the next step is to synthesize approaches for integrating ML into the MSA system. The space for integrating machine learning into MSA systems is quite extensive and can be utilized for many different scenarios, but four main integration areas can be highlighted: system load forecasting model, system productivity degradation prediction model, system protection model, system resource planning model, system load forecasting model. With the help of ML, a model can be trained using various features such as critical microservices response time and used to detect patterns in the operation of the MSA system. Similar to the circuit breaker, this model can promptly determine whether a microservice is under heavy load and address this issue before it becomes critical and starts negatively impacting other microservices. System productivity degradation prediction model MSA systems may experience varying loads and errors during specific times and periods. For instance, an MSA system may encounter spikes in requests during certain periods, such as holidays and seasonal events, when the number of users can sharply increase. By allowing the model to learn and understand the MSA system and how it operates over time, we can prepare the model to better detect anomalies and prevent false positives. System protection model. The third area of ML application is system security. In the era of cybersecurity, it is important to have the ability to protect your MSA system from targeted attacks. By studying the behavior of your MSA system, the model can predict and detect attacks that may threaten the security of the system. System resource planning model. The fourth area of ML application is system resource planning. As the system grows and evolves, it is important to properly allocate resources and adapt to the system's needs. With machine learning, it is possible to learn which services require more resources and how much resources are needed for effective system scalability. Conclusion. The integration of machine learning ML with microservices architecture improves system efficiency, decision-making, and real-time adaptability. The findings provide a foundation for future developments in intelligent system scaling.